our topic magnetic materials. This magnetic materials is one of the topic in second unit. Okay, what is the magnetic material first? Magnet means which shows the attracting property, that is called the magnet. Okay, in this magnetic materials, this is some definitions. Magnetism, the attracting property exhibited by the magnet is known as magnetism. Dipole, magnet has two dipoles, north pole and south pole. These two poles separate a finite distance. Magnetic moment, magnetic moment is the product of magnetic pole strength and distance between two poles. 2L, M into 2L is called the magnetic moment. Another definition for magnetic moment is if electric current I flows through a circular wire. Suppose this is the circular wire. You flows the current through this circular wire having the area of cross section A. The product of these two, current and area of cross section, is called the magnetic moment. So we have two definitions. One is product of pole strength and distance between two poles, and another one is current into area of cross section. Mind these definitions we use later. Magnetic field, the space surrounding the magnet. The space surrounding the magnet up to which its attracting influences is felt. Where the attracting property shows, that space is called the magnetic field. Magnetic field strength. Magnetic field strength is the force experienced by a unit north pole. Force experienced by a unit north pole placed at a given point in a magnetic field. Force experienced by a unit north pole placed at a given point in the magnetic field. Magnetization or intensity of magnetization. Magnetization, the magnetic moment per unit volume is called the magnetization. Magnetic moment per unit volume is called the magnetization. Units of magnetization is ampere per meter. Susceptibility, the ratio of magnetization produced in a sample to the magnetic field strength. The ratio of the magnetization produced in a sample to the magnetic field strength is called magnetic susceptibility. There is no units. Chi is equal to M by H. Susceptibility equation is chi is equal to M by H. Magnetic lines of forces. The next definition, magnetic lines of forces. The magnetic field is characterized by magnetic lines of forces. See here, this is the magnet. This magnet, it produces a magnetic field around this magnet. This magnetic field is characterized as magnetic lines of forces. This magnetic field characterizes these lines. These lines are called magnetic lines of forces. Magnetic induction field strength or magnetic flux density. Magnetic induction field strength or magnetic flux density, the magnetic lines of forces passes through unit area of cross section. Suppose this is the unit area of cross section. The magnetic lines of forces passes through unit area of cross section is called the flux density. Here suppose flux is pi, area of cross section A, B is equal to pi by A. Units of this magnetic flux density is Weber per meter or Tesla. Magnetic permeability, it is the ratio of the magnetic flux density and magnetic field strength, and it shows the amount of magnetic lines of forces penetrating through a material. Throughout the material, how many magnetic lines of forces passes through? The amount of magnetic lines of forces passes through in material is called the magnetic permeability. Mu is equal to P by H, V is equal to H, and magnetic permeability of free space. Suppose you take the material is air medium, air, then we call that permeability is called the magnetic permeability of free space. Mu naught is equal to B naught by H. Relative magnetic permeability. relative magnetic permeability, it is the ratio of permeability of the material to the permeability of the free space. Then we said that is the relative permeability. We get is mu r. Mu r is equal to mu by mu naught. Next topic, relation between B, H, M. Here B is the flux density, H is the field strength, and M is the magnetization. We give the relation both three. Generally B is equal to mu H, that means mu is equal to B by H. B is equal to, in place of mu we write mu naught mu r. B is equal to mu naught mu r H. Here we add mu naught H and subtract. There is no change in the equation. But M is equal to H into mu r minus 1. In these two terms, we take out mu H. In these two equations, we take out mu naught H, remaining term mu r minus 1 plus mu naught H. In place of that H into mu r minus 1, we write M, and the remaining term mu naught H. In these two terms, we take out mu naught. B is equal to mu naught H plus M. So this is the relation between B, H and M. Relation between susceptibility and permeability. Another relation, B is equal to, in previous equation we obtained B is equal to mu naught H plus M, and mu naught is equal to B by H plus M, and relative permeability mu r is equal to mu by mu naught. Mu is B by H, mu naught is B by H plus M, H plus M by H. Here 1 plus M by H. M by H is the height, that is the susceptibility. So mu r is equal to 1 plus chi. So this is the relation between permeability and susceptibility. Okay. Next, we are going to another question. Very important. Origin of the magnetic moment. Origin of the magnetic moment. Magnetic moments are present in every body. How they produce the magnetic moments? In this question, we know how the magnetic moments are produced in that body. Materials are made up of atoms. Generally, materials are made up of atoms. This is the atom. Okay. In this atom, at the center nucleus, electrons revolve around the nucleus in an orbit. Okay. And electron also rotated, spin its own axis. All of you know this one. In atom, at the center nucleus, and electrons revolve around the nucleus in an orbit. Yes. And this electron again takes spin in its own axis. So electron revolve around the nucleus means electron takes movement. Electrons move here in an orbit. Yes. When electron move in this orbit, that means movement means current produced. Movement of electron, flow of electrons is nothing but current. When current flow in this direction, automatically magnetic field develops in this direction, perpendicular to the current, because both electric field and magnetic field perpendicular to each other. That's why here magnetic field developed. Magnetic field developed. Hence we get orbital magnetic moment of electrons. So electron move in an orbit. Due to the movement of electron in this orbit, magnetic moments develop. Those magnetic moments are called orbital magnetic moment. Next, spin magnetic. Again, the electron spin in its own axis and rotate around the nucleus. Due to this spin also develop magnetic moments. Those are spin magnetic moments. And And the next one, nucleus also spin. Due to that spin also, the magnetic moments are produced. These are the origin of the magnetic moments developed in the materials. So first we go to orbital magnetic moment. In orbital magnetic moment, consider an electron of mass m. We consider an electron having the mass m charge e revolving around the nucleus. R is the radius of the orbit. V is the linear velocity of the electron. Omega is the angular velocity. Then the linear frequency is equal to omega by 2 pi. Because omega is equal to 2 pi n. N is equal to omega by 2 pi. Time period of the revolution t is equal to 2 pi by omega. Because 1 by n, because time period and the frequency both are inversely. So frequency is equal to omega by 2 pi. Then time period of the revolution is equal to 2 pi by omega. Current I is equal to charge by time period. I obtain I charge by time period. Here charge of the electron is E and time period is 2 pi by omega. The area of the orbit is A is equal to pi r square. Then magnetic moment, already in the previous definition, so the magnetic moment mu m is equal to I into A, IA. Here I is the current, this is the current, E by 2 pi by omega, and the area is pi r square. So we substitute here E by 2 pi omega pi r square. We obtain E omega square by 2. So this orbital magnetic moment is pointing from south pole to north pole. Here obtain the magnetic moment due to the electron revolve around the nucleus in an orbit. The angular momentum of the revolving electron is given by general angular momentum is equal to linear momentum into radius. So mv is the linear momentum, radius is r. Generally we know v is equal to r omega, then we m omega r square. Mu orbital is equal to, in previous we obtained mu orbital is equal to E omega r square by 2. This is where we can write like this, E by 2 m omega r square. In place of m omega r square we write angular momentum mu orbital is equal to E omega r square by 2, E by 2m into m omega r square. In place of m omega r square we write angular momentum. So orbital angular momentum minus indicates both orbital angular momentum and magnetic moment. Here momentum, that is the moment, both are opposite direction, that's why here we take minus. The ratio of these two, orbital angular momentum and magnetic moment, is called the gyrometric ratio. Gyrometric ratio, gamma is equal to E by 2m. According to the modern atomic theory, the angular moment of an electron in the orbit is determined of the orbital angular momentum, indicated L, that L is equal to h by 2 pi. In place of orbital angular momentum we write L h by 2 pi, then minus E h L by 4 pi m. Here E h by 4 pi m is the mu b. This is the fundamental unit of magnetic moment. This is the constant value. E h by 4 pi m is the constant value. So this is called the magnetic Bohr magneton. Bohr magneton. Magnetic moments measure with this unit Bohr magneton. So L vary 1, 2, 3. So orbital magnetic moment Bohr magneton value is 9.27 into 10 power minus 24 ampere meter square. So this is the orbital moment. Next, spin magnetic moment. Spin magnetic moment. Electron spin its own axis. When it revolves around the nucleus in an orbit, it takes its spin in its own axis. It establishes a magnetic field and we get a magnetic moment. That magnetic moments are called spin magnetic moments. mu spin is equal to barometric ratio by E by 2m into S. Here S is the h by 4 pi. H by 4 pi. This value is 9.4 into 10 power minus 24 ampere meter square. Another last magnetic moment, nuclear spin magnetic moment. In addition to electronic contribution, nuclear spin also contributes the magnetic moment of atoms. Nucleus also spin, that's why they that give the magnetic moment. Mu nuclear spin is equal to h by 4 pi mp. That value is the 5.05 into 10 power minus 24, 27 ampere meter square. So finally, magnetic moments are obtained mainly three causes: orbital magnetic moment, spin magnetic moment, nuclear spin magnetic moment. Okay, these are the three causes to produce the magnetic moments in every body. Any body, you take any body, you have some magnetic moments, but its magnetic material are not. We decide their alignment because of their alignment. Due to those alignments, it is magnet or not. We decide. Okay. Next, classification of magnetic materials. Under 10 marks question, magnetic classification of magnetic materials. Classification of magnetic materials. Okay. Magnetic materials are classified in 5 types. First, diamagnetic material, paramagnetic material, ferromagnetic material, antiferromagnetic material, ferrimagnetic material. So we have 5 types of magnetic materials: dia, para, ferro, antiferro, and ferrimagnetic materials. We discuss individually. Diamagnetic materials. An electron moving around the nucleus resists magnetic moment due to different orientations of various orbits of an atom. Orientations of various orbits of an atom. Different atoms, different gives the magnetic moments, but the total net magnetic moment is zero. In the absence of magnetic field, their orientations are different. The magnetic moments different orientation, having different orientations. Totally net magnetic moment is zero. When we give the magnetic field or we apply the magnetic field, all the magnetic moments of atoms will align in the opposite direction to the applied field. Opposite direction to the applied field, those are called the diamagnetic materials. Okay, the relative permeability of diamagnetic material is less than 1. Susceptibility is negative because those align opposite direction to the field. Phi is independent of temperature. Examples of diamagnetic materials are organic materials. See here, alignment of magnetic moments opposite to our applied field. Then there is no susceptibility. So susceptibility is negative. These are not independent. This is susceptibility independent on temperature. Examples of diamagnetic materials are organic materials. Okay. Next to paramagnetic material. Each electron in orbit having the orbital magnetic moment, spin magnetic moment. When shells are unfilled, there is no magnetic moment. In the absence of external magnetic field, the net magnetic moments of atoms are arranged in random directions because of thermal fluctuations. As there is no magnetization. Okay, we take two magnetic moments, orbital magnetic moment and spin magnetic moment. If there is no magnetic field, they are arranged randomly. They are arranged randomly. When you give the external field, the magnetic moments align in the direction of the applied field. The induced magnetism is the source of the magnetism. Relative permeability. Relative permeability mu r minus 1 greater than 1. Susceptibility is low and positive. Phi is equal to C by D, where C is the Curie temperature. Example, alkali metals and transition metals. See this, if there is no applied field, the atoms are arranged randomly, the applied field, they are aligned regularly but in the direction of applied field. In the diamagnetic materials, they are arranged in opposite direction of the applied field. But in paramagnetic materials, those are aligned in the direction of the applied field. That's why here having the susceptibility but low and positive. When you remove the magnetic field, those are arranged randomly. But you give the magnetic field, they are aligned along the direction. When you give the applied field, that's only they behave like a magnet. If you remove the field, they become a diamagnetic general material. Okay. So we see the temperatures graph, susceptibility and temperature here gradually decreases. If you take 1 by T, linearly propagate, linearly increases. Okay. Next, ferromagnetism. In ferromagnetic substances, the permanent magnetic moments is mainly due to the spin magnetic moment, which will be aligned parallel to each other. Here, the magnetic moment, magnet is exhibited by the spin magnetic moments. Permanent magnet is exhibited by the spin magnetic moment. When you give in the absence of external field, they exhibit magnetization. If you give the field to that magnetic materials, they are aligned, the magnetic moments present in that material are aligned regularly in the direction of the field, and you remove the field, they are aligned same. In the absence of external field also, they exhibit the magnetization. This is due to the spontaneous magnetization. There is a special form of the interaction called exchange coupling. In between, those moments, they have some interaction that is called the exchange coupling. Due to the exchange coupling, they maintain spontaneous magnetization. Okay. Relative permeability, you are much greater than 1 because of having the interaction between those two spins, having high permeability, high susceptibility and positive. Example, transition and parallel earth metals. Phi is equal to C by T minus Tc. T minus Tc. Tc is the Curie temperature. Here Curie temperature is, suppose temperature increases, susceptibility decreases. At a particular temperature, ferromagnetic materials become a paramagnetic material. The temperature is called the Curie temperature. How the magnetic materials, ferromagnetic materials shows the spontaneous magnetism. See this diagram. Without magnetic material, without magnetic field, the magnetic moments are arranged like this. Spin magnetic moments. We take here spin magnetic moments. When you give the magnetic field, weak magnetic field, here the domains, those magnetic moments are arranged in domains. These are called the domains. These domains expand or sink, then you give again field to that material. Those are aligned parallel to each other. Here are aligned parallel to each other, and you remove the field, the arrangement are not changed. So that's why they maintain permanent magnetization. Anti-ferromagnetic materials. The materials with anti-parallel magnetic moments are known as anti-ferromagnetic materials. Net magnetic moment exists in the direction of the applied magnetic field. Relative permeability greater than 1. Susceptibility is low and positive. Phi is equal to C by T plus Tc. Temperature. This is the, see here, the spin alignment. Both are anti-parallel, anti-directions. Parallel but anti-directions, they are aligned. Here in this graph, when temperature increases, susceptibility increases at a particular point. All of a sudden, they gradually decreases. Where that susceptibility suddenly decreases, the temperature is called the knee temperature. near temperature. Next, ferrimagnetic materials. The substances which consist of anti-parallel magnetic moments of different magnitudes are known as ferrimagnetic substances. Anti-parallel and magnetic magnitudes, different magnitudes. Relative permeability much greater than 1. Susceptibility is high. Example, ferrites and chi is equal to C by D plus or minus AC. See here, the alignment of moments, spin moments, parallel. So susceptibility high is high and positive. See in this diagram. Ferrimagnetic materials, the magnetic moments are aligned, anti-parallel, and having the moment magnitude different. See here, different magnitudes and anti-parallel are aligned. The type of magnetic materials are called ferrimagnetic materials. Relative permeability mu are much greater than 1. Susceptibility chi is high and positive. And example, ferrites, chi is equal to C by D plus or minus Dc, where Dc is the Curie temperature. So these are the 5 types of magnetic materials. Number 1, diamagnetic, paramagnetic, ferromagnetic, antiferro, ferrimagnetic materials. This question is very important